So good morning. I apologize for the technical difficulties before starting. But I'm glad to be here. I'm glad to be here at MathCon for a second year in a row presenting, which is very fun. And today I'm here to talk about a concept known as topological distinguishability. And I feel like it can be a daunting topic at first, but I feel like it applies back to a lot more concrete concepts, and I think in a really nice way. And so to start, just to know that generally when you think of metric spaces or spaces in analysis and in topology as well, almost all of them are what is known as T0, which means that if you grab any two distinct points, any 2 points in your space that are not equal, you can find at least one neighborhood where one does not contain the other. And then that means they are distinguishable. But in topology especially, there are an entire class of spaces that often are ignored that do not have this property, where there are multiple points that share all the same open neighborhoods in your topology, which, if you don't know, is what we call the tau in this notation of the topological space. And so for this reason, you won't see non-T0 spaces studied as much. Non-T0 spaces lose a lot of your intuition associated with continuity and metrizability, because obviously they lose their ability to be metrizable if they lose the distinct point, that property. And then on the topic of metrizable spaces, for future reference, just recall that your metrizable spaces are what are called T1, which means if you have 2 points in your space that are not equal, they can be separated by neighborhoods. They have countable bases, which means that you can use that among your base set, your basis of that topology is countable, and they're also regular, which means that your closed sets, any arbitrary closed set, can be separated by an open neighborhood. And these metrizable spaces provide a well-behaved framework for these ideas of continuity, limits, and derivatives. And so going forward, the idea and the question I want to ask is, can we somehow bring some of this intuition to our non-T0 spaces? And how can we use identification to understand these spaces better? And so moving forward, here are a few examples. And so a trivial example of a non-T0 topology is going to be your indiscrete topology. So when you only have in your topology the empty set and the entire set as being open. Obviously, any element in that set, they're all going to be in the same neighborhood, which is the entire set. Another time where you see T0 spaces is when you identify points together. So for example, when you see a circle defined in a topological sense, you tie the points 0 and 1 together, and naturally then they come to share the same neighborhoods. And so you technically lose T0 in some cases. But in working downwards in our spaces, obviously, the nicest example, and the one that you see in analysis, for example, is R2. This is a metric space. You can quantify distances between points with a metric. A common example of a T0 space is what we call the Sierpinski space, which you can see here. If your underlying set is 0 and 1, 0 has a neighborhood that does not contain 1. So these 2 points remain distinguishable. And then the indiscrete, they both share the same neighborhood, so it's not T0. And just to talk about an applied sense really quickly, where this sometimes can come up in computer science is when you look at data sets. If you have your data set which contains some sort of parameters, so we say n parameter tuples in a formal sense, they can be viewed as a collection of points in some sort as a subspace of Rn. And if you end up getting the same observations multiple times, if you consider a topological space on just your data set points, obviously your points where you have your same and identical observations, they're going to be the same topologically. They're not going to be distinguishable. And this does come up sometimes in machine learning, especially in the realm of clustering. A lot of times, data sets will remove duplicate points when clustered, and it turns out back in the realm of topology, we have sort of an identical operation that kind of represents this process, which is kind of interesting. And so, kind of a figure here, you see that kind of the blue and the red. I try to make them look like they're in kind of the same spot, and they share the same neighborhoods in that context. So, and then back, let's now talk about, since you know what it means to be T0, what it means to be not T0, let's talk about distinguishability one more time in a formal sense. And so we could express a space to be T0 is when all unique pairs of your points are going to be distinguishable. They have to be a small neighborhood that separates them. And so formally, as I said before, you want to look for a neighborhood in your topology where A is in 1 and B is not in 1 or vice versa. And the question then becomes, is there a way to convert our non-T0 spaces into T0 spaces? And the answer turns out to be yes, we can. And the way we do this is with Kolmogorov quotients. And so we're gonna start by constructing an equivalence relation. We know what it means for our points to be distinguishable, and we know when our points are not. And simply, if you get the inverse definition, it's just if all the neighborhoods in the topology that contain 1 imply that the other one is also in it. And so we're gonna call our relation E, just for the sake of simplicity. And let's construct a relation to be the ordered pairs where for all x and y in our topological space, x and y is in that relation if they're not distinguishable. And so what does this relation end up being when we identify these points together when they're not distinguishable? And so recall that our equivalence relations must be reflexive, they must be symmetric, and they must be transitive. And it turns out this process of picking out indistinguishable points and grouping them together with an equivalence relation is going to end up being an equivalence relation, which is really interesting. And one proof for this entire presentation, this is the proof for it being an equivalence relation. Obviously, it's going to be reflexive because if you consider a single point, obviously a point X is going to have the same neighborhoods as itself. That's a pretty straightforward process, and so X is related to X in our relation. Then, for symmetry, if we considered X and Y to be 2 points in our topology, and then for all the neighborhoods in T where X is in it and implies Y is in it, since saying if and only if, in this case, the double arrow is a symmetric relation, it works the other way too. If Y and N implies X and N in a two-way sense, then that means this is symmetric. And then for transitivity, it works in the same way. Because we're saying that if X is an N, then Y is an N in a two-way sense, and when it follows for Y and Z, that means all the neighborhoods that X are in, Z is in. And so this is a very simple proof based on the logical construction of the if and only if relation. And so with this in mind, and with this equivalence relation, let's talk about what it means to apply this to a topology. And the process of this is called creating a quotient topology over our initial set. And so with our constructed relation E, we can form a new topology. And recall that on a regular set without a topology, your equivalence relation breaks it up into partitions. That is a disjoint union of subsets of X where if A and B are in the same partition, they are related to each other. And so where Y is the family of unions of these, or since it was the family of these partitions, we can then create a surjection that maps every element in our base set to its equivalent class. And for here, and we'll use it again a little bit later, we call this relation eta. And so eta, all we're doing is we're talking about taking a point in our topology, and we're mapping it to its equivalence class in Y, which is our family of partitions. And this creates the identification topology of X by the Kolmogorov quotient. And this, once again, can be viewed as the application of eta to every single element in X. We're basically going element by element and saying, okay, is this distinguishable from any other point? If so, then it gets put in that equivalence class. And we keep doing this over and over again. And what we get is a T0 space on the equivalence classes of X. And now with this in mind, there's a really interesting place where this applies to, and that's in the realm of pseudometric spaces. And so we're gonna jump a little bit here to pseudometric spaces, but we're gonna see that this is very closely related to the idea of the Kolmogorov quotient and identifying non-T0 spaces to be T0. And so if you take an analysis, if you've taken graph theory, you've probably seen a distance metric before. And recall that for an underlying set X, you can define a distance metric, a function is a distance metric from that set to R if the distance is greater than 0 or it's non-negative. If it being 0, or if the distance is 0 between any 2 points, that implies the 2 points are the same, essentially. the symmetry of that function, and then the triangle inequality. And so the question becomes, what happens if you drop that second requirement, where any two arbitrary points do not have to be equal for them to have a distance of 0? And this turns out to be what we call pseudometric spaces. And these come up a lot in like functional analysis with some semi-norms. And so naturally, these requirements for a pseudometric space, since we're dropping one of the 4 axioms, one of the 4 properties here, to be a metric, obviously these requirements are going to be a lot less than a metric space. But the question is, can we figure out a conjecture for what properties this space must have? And this is our goal here. And it turns out that we actually can. So moving on, once again talking about examples, as I said before, pseudometrics appear a lot in functional analysis. For example, here's an example of a distance function between points in a function space, where you're basically just subtracting the function at the point C from another function. And this can be 0 when the functions are not equal, because that just means at that individual point, the 2 functions share the same output value. And so obviously this is going to be a pseudometric, since this being 0 does not imply that the 2 functions are equivalent to each other. And in functional analysis, any semi-norms on your vector space are going to be pseudometrics, and that's kind of interesting, I feel. But when you have a pseudometric, what's interesting is that you can create a metric space out of it. So let's call X and rho our pseudometric space. It doesn't matter what the actual underlying pseudometric is. What happens if we then take that space and identify the underlying topology? That is, we're identifying the base set and leaving the relation. So the distance between any arbitrary points or pseudometric becomes the canonical surjection. We define the 4 as being eta. So we're doing our pseudometric on the identifications of X and Y. And so if in our pseudometric, if this is a 0, that implies that they are indistinguishable topologically, which then implies that they're going to be put in the same partition of our set. So these 2 points are now equal in our new topology, in our new underlying identification space, which then means that their distance is still 0, but it holds up as a metric space since they're the same point now in our new topology. And so rho becomes a valid metric when you identify the underlying space using Comte-Gauss quotients. And this kind of provides some interesting properties. We'll have some information about the properties of pseudometric spaces for this to be able to work every single time in an identical manner. And so, really, what I want to touch on is a potential conjecture on the requirements of a space to be pseudometric. And specifically, we're talking about sufficiency. We're talking about if it holds these requirements, then it is pseudometrizable. And so, once again, as I said at the very first slide of this presentation, recall that every metrizable space is going to have a countable basis, it's going to be regular, and it's going to be T1. Once again, regular is the closed sets being separated by open neighborhoods, and T1 is the individual points being always separated by open neighborhoods. And so so when we're identifying from a pseudometric space to a metric space, all we're doing is we're putting the points together. We're putting the points that are indistinguishable in the same equivalence classes. And so my thought is, what if we consider the properties of this? What properties would it still have? So if we consider regularity and second countability, these extend directly to T1 spaces, and these likely would still have to hold in our pseudometric space for that identification, that function, that identification to work every time. And so the only thing that we have to consider here is what happens when we lose T1, because we end up losing T1 in a non-T0 space, because obviously any 2 points that are indistinguishable in our non-T0 space, they're going to have the same open neighborhood. They're at the same neighborhoods, so you can't separate them at all. So we lose T0. But it turns out in non-T0 spaces, we can define what's called symmetry, which is the idea, which is essentially the T1 axiom, but over distinguishable points. So we say that any 2 distinguishable points are in R0 have neighborhoods that do not contain each other, which covers the case where our which covers the case where our points are not distinguishable. We end up creating, we have essentially going around that definition. And so I conjecture based off of the fact that we can create these pseudometric spaces using equivalence relations from pseudometrics that you likely need to maintain regularity, civic accountability, and then symmetry among our distinguishable points for it to be pseudometrizable. And I think that's really interesting how you can kind of come up with these hypotheses from a seemingly unrelated idea here. And that's where I want to leave off. And so in the preparation of this presentation, I used mainly this literature review that my advisor would be very happy to hear is from an Estonian graduate student on common graph quotients. And then studying analysis was also a big part in preparing this. And so I thank you for listening to me talk. Any questions? Oh, yeah.
What thoughts do you have for your future work?
In this, I've been trying to understand, metrization theorems better because obviously the baseline requirements for the metrizable space, these were derived by Uriso in like the 1920s using his metrization theorem as being necessary and sufficient requirements for metric spaces. And so as of recently, I've been trying to understand, if the pseudometric spaces need to maintain these same sort of ideas, can some of the framework of that theorem then apply to pseudometric spaces? But that's also a lot more of a difficult question than initially thought.
And I know that's future work, but you sort of have thoughts about how you're going to start attacking that.
I might be getting this a little bit wrong, but when you're considering the metrization theorem, what you're doing is you're creating an embedding from your metric space into, from your proposed metric space into another space, which is a metric space essentially. And so the idea is, can you use embeddings to do a similar thing for two metric spaces or not?
Thank you.
I have a question.
Yes.
Have you looked at all at, so I study rings of continuous functions, so this has a natural question that if you start with an X and you look at the set of all continuous real valued functions or complex value, you get a ring under the usual component-wise operations. I'm guessing, but have you looked at all that, like, if you look at C of X and then C of the identification of X, is there any difference between those two rings?
I have not actually, and that is a really good question. And I believe actually because the review I was using, the common graph quotient actually gets into algebraic topology and the using of groups and stuff to kind of understand these quotients. There actually might be some more information there on that kind of work. Anything else? Oh. Once again, I thank you all.